next methods, the next set of solution finding methods. Now, since you are not ready with your function models, we can't do practice on FOS in this class. We move to the next method of solution finding, which is called inventive principles. Inventive principles, hopefully we should be able to do practice, because the first level of inventive principles does not require any further preparation. You just need to know the problem statement. If you know the problem statement well, if you have analyzed, if you've collected sufficient data about your problem statement, you should be able to apply inventive principles. Okay. If you've not even done that work, then in the breakout rooms, you will struggle. You will not be able to apply these solutions also. So what are these inventive principles about? So remember, we talked about, this is a repeat slide. When in the second lecture, when I had introduced introduction to TRIZ, when I had introduced TRIZ to all of you, the same slide was there even then. So typically, most of our problems are contradictions, where we want to improve one parameter, let us say area, and another desired parameter degrades. So it's kind of a seesaw. You want to improve one, the other one would go down, and you now are just playing around, striking a balance. Oh, I want to improve the area this much, but the speed should not go down. So how many of you have played on a seesaw? Just one person has played on a seesaw? Okay. Thankfully, huh? You guys have played. So how easy or difficult it is to strike a balance? Oh, just exactly in the center. Is it easy? A little wind blows and you again struggle. You again have to set back, come back to the center all over again. So in this method of applying inventive principles, what we are looking at is that neither speed nor area, so neither of the two desired parameters, should get compromised when we are finding a solution to the problem. How is this possible? See, in reality, what happens is, as soon as I increase reduce the area, the speed degrades. So all my energy is then focused on, oh, how to reduce the area only this much that my speed remains acceptable. That is where we struggle. By using these inventive principles, we could bring in other parameters which we were otherwise ignoring. For example, stability, or for example, accuracy, or for example, power. Or throughput. So there could be something else which we could trade off, which is not really that desired a parameter as of now in the system. So the inventive principles help us to identify those alternate parameters which may not be as desired as the first two parameters are, and we could compromise on those parameters. We could compromise on complexity a bit, and by that we could gain area and also speed simultaneously. So that is what the application of inventive principles does for us. So what Altshuler did was he identified those 40 inventive principles and built a 39 cross 39 matrix of such desired parameters. And in that matrix, in every column, in every cell, he wrote the parameters which were he wrote the inventive principles which were statistically relevant and which were used most commonly to solve the problem there. So, do you remember a few inventive principles that we have talked about? Anyone? We talked about quite a few. Sorry, please.
Trimming.
No. Trimming is a method. Trimming is a tool. Trimming is not an inventive principle. Contradiction. Contradiction means that, okay, I have wanted to improve area, but my speed degraded. So it's a contradiction. How do I handle it? Inventive principles.
Sir, One was there like predicting markets to come up with new technology.
That was another tool theory. Trends of engineering system evolution. Okay, so I get it. You are missing the thing in a big way. You remember these? We talked about segmentation. We talked about equipotentiality when we talked about how ships crossed the Panama Canal. Remember the Panama Canal story we discussed, or we did not discuss?
Yes, I will remember.
So these are some examples of inventive principles. Segmentation, for example, and it is so commonly used across various design places. We talked about segmentation in terms of a bicycle, that the chain of a bicycle, the iron chain is segmented into small nuggets so that your chain becomes flexible. Uh, for circuit designers, I would say, SRAM, in SRAMs, bit lines are broken into smaller bit lines so that you gain speed and power. Pipelining for computer architects and others of us, pipelining, we segment a big activity into small chunks and run all of them in parallel so that the overall throughput of the system increases. We can segment algorithms into small parts which can only be accessed conditionally. So these small parts, they run faster and also help us in doing multi-threading and multitasking and all that. Asymmetry. I think we discussed this also, that are the CPUs the application processors that you have in your cell phones. They use this big little multi-core architecture. There are 4 big cores and 4 small cores, or 2 big cores and 4 small cores, or 6 small cores. So that you're most energy efficient, but you're also able to get the power to solve big complex problems when you need it. So these are some inventive principles which are very commonly used. Merging, load sharing facility or supercomputers. How are supercomputers made? A lot of small computing elements, they are brought together, they share the workload, and they have a supercomputing power. Universality. One thing takes care of many other functions. For example, fiber to the home enables high-speed internet, can also carry telephone signals, can also carry cable signals and everything. So in Delhi, many of you might already be using FTTH, and that is universality. One thing, but does many functions. Local quality, how to improve something in a local small method. Lunch boxes can have separate compartments for hot food and cold food. Equipotentiality, Panama Canal, we already discussed, or things like homomorphic encryptions, those of you who are working on security, or decoupling capacitors, those of you who are working on circuits. Other inventive principles, common ones, dynamicity, change the way the system is operating. We use it in aeroplanes, we use it in chips where we talk about dynamic voltage and frequency scaling. You can, YouTube, when it senses that your bandwidth is low, it automatically reduces the resolution of the video as it streams it to you. So we see this dynamicity principle also very commonly used. Periodic action, power hammer. So very light in nature, but still gets or hits nails, or drives nails into very hard surfaces also. Intermediaries, bubble packs, packing materials that we use, they are intermediaries so that your product does not get the shock. Self-service, edge computing, intelligent systems, perpetual modes, sensor modes, auto defrost refrigerators. So if you have any questions you do not remember or know about any of these technologies, please do ask. Use of copies. How many have heard about RAIDs, the redundant arrays of independent disks? Many of you are computer engineers. I assume you would know about it. RAIDs. No one? Okay. Someone. Mirror websites. All of us serve the internet. We know mirror websites. To improve customer experience in terms of the website loads very fast, because the closest mirror is where the data comes to you from. Adding another dimensions, Xbox joysticks, 3D transistors, Google Drive. So you don't even have that drive on your disk. You just go to cloud, and that's a different place. Your data is stored elsewhere. So all of this we know about. So these principles, we've been using them day in and day out, using the benefits of these principles day in and day out. How to implement them to solve the problem at hand. That's the big thing. Are you with me? So, till now, what I've done is I've not even shown you 40 inventive principles. I've just told you that whether you know it or not, you're already reaping the benefits of these inventive principles. The problem statement for us now is how to systematically apply and choose the right inventive principles for the problem that I have at hand. Am I right?
Yes, sir.